Okay, so applications of sinusoidal functions, example 3. Emma's going to teach this one. Not even listening to that. Bacteria is the new black, right, every day. Well, your body's actually covered in bacteria. It's like an acetobacter. So, you can... All right, so sunrise and sunset times in Calgary are shown in the table. January 1st, February 1st, etc. Now, you can't put in January, February, so we're going to go by day number. And then it gives the time of sunrise. Now, since Alberta switches from standard time to daylight savings time, we're also going to have to adjust the time, right? I mean, it would have been a lot easier just to use Regina or something, right? Because they don't switch times. But this is what we have to work with. We're going to assume it is not a leap year, so it's not next year, so it's this year, or 2017, or 13, or 14. So we need to fill in this table. So like how many days in March? There are 31 days in March. Okay, so then what number is going to go in the table? It's the day number, right? So January 1st is day 1. So, actually we got to do...
How many days in February?
28 days in February, so March 1st will be day 60. 60, so I was getting ahead of myself. Then, 31 days in March, so April 1st is 91. And then April has 30. Oops. And then May has... No, May has 31.
Yeah, 31.
You know you can do it on your knuckles?
Yeah.
January, February, March, April, May, June, July, August. If it's a bump, it's 31, which is the following. That's February, there's 28, 29. Okay, so May has 31, so this will be day number.
It says assume now.
Assume what?
No leap year.
Yeah, so we didn't add 29 days in February, did we?
Oh, okay.
We're long past that. We're in June, man. June. Okay, June has how many days? 30. July has 31, so there'll be a 3 there, and a 1 there. And August has 31, and we got a checkpoint here, right? 244, good, that's what we would have got. Okay, and September has 30 days, has September, April, June, and November, all the rest got 30. Come on, there's enough things out there for you to know. It's got 30 days in September. October. When's Halloween? Come on, seriously? Every small child should at the very least know that October has 31 days. Too bad you're not a small child. Okay, and then December 1st, November is 30 days long, so 335 for December 1st. Okay, that was the easy part. Now comes the hard part. So what we need to do is convert time. Now time is in hours and minutes, right? We got to convert that to a decimal time. So 840 is 8 hours plus 40/60ths, right? Or 8.67. 812 will be 8 hours plus 12/60ths. So 8. $7.20. You almost don't even need, I mean, it's a third of an hour, right? So it's 0.33. Then comes April to switch to daylight time. And so 7:11 daylight time is 6:11 mountain. So now we have to subtract an hour, right, to go into a standard time zone. we have to subtract an hour and then do the conversion. So 609 Mountain will be 509, or sorry, Mountain Dale will be 509 Mountain Standard, right? And then I might need a calculator for that one. And this will be 4. Well, I need those numbers, so yeah, I guess I'll have to do it. I could do this part because it's like subtracting 1. I can handle that. Right, I said in Saskatchewan you don't have to worry, they stay on standard time all year. And then in December, because November we make the switch back, right? So that's going to happen not this weekend, but next weekend. We shall fall back. Gives you an extra hour of sleep. So there's a whole bunch of preliminary work, right? Like we're not even got to the real, just what the heck are we doing? Well, we're going to run a sinusoidal regression and come up with a model for sunset times. I'm guessing those are all like PM times. Should have used 24-hour clock, really, right? But, yep.
Why is the last one 8%?
It says
So sunrise and sunset time. What's it? How is the sun? What? Sunrise and sunset time. That makes no sense. For 9 days in Calgary are shown. No, the time of sunrise is shown in Calgary for the year. I don't know how the example.
It just says AM.
Last one should be
Does it?
7.
Oh right, AM. Yeah, but this sunrise and sunset times, like no. Sunrise Calgary. YYC.
Last one should be 7.
No, it shouldn't. It's Mountain Standard Time.
Oh, it's already in 7.
Okay, so what do we get here? 5.15? 4.60?
8.
8? Give it a belt. Nice belt. What did the 0 say to the 8? Nice belt. 431? 452? 449? 82? 540? I could do that. It's like 5.67. 638? 63? 0.50. And 832. Okay. Boom. Okay. So that's some preliminary work, right? And sometimes when we collect a set of data, we have to do some manipulation to it ahead of time, right? We got to sort of standardize it. Complete table, blah blah blah. 2 row. Okay. 1 cycle of sunrise time. So how long does it take to go through a cycle of sunrises? So we want to look at these times, right? Not this, because this goes mountain. So we're starting at like 8.67, and then it's going down, and then it's going back up again. When's it going to get back to that? It's not quite there. Probably around the end of December, January. How long is that? A year. So 365 days. Plot the data using the graphing calculator by entering day number for L1 and sunrise time in hours in L2. Okay, so this sunrise time in hours after midnight in Mountain Standard Time. State an appropriate window for the data. Such graph appears discrete for one complete cycle. Okay, so I'm going to pause this because. Okay, so your data is in the list, and then it's a good idea to check the list before you do any questions, especially having just entered 24 numbers. So just scroll through them again, and if you look down here, it's easier to see the numbers that you've entered than if you look up here. Okay, so it's 6.18, and it's just checking, make sure that they're correct, make sure that the days are correct. Okay, if you want to look at the data, so we set a window. We chose 0 to 390. by 30s and 4 to 9 to cover everything off. We went second y equals, we turned on the stat plot and then hit graph. That's what we've got. So now, plot the data and sunrise time, show an appropriate window, we've done that. So the graph appears in one complete cycle. We have maybe a smidge more. Determine the regression equation, state the equation below. Parameters rounded to the nearest hundredth, where t of n represents the sunrise time in hours. So we're going to be writing t of n, sunrise time, as a function of the day number. And to do this, we're going to go stat calc. The sign regression is closer to the bottom, so I arrow up. Depending on your calculator, if you have one of these guys, if you have an 83 or one that doesn't have this menu, just go sine reg y1. And on this guy, we'll just arrow down and say store the regression equation in y1. So we can do an out. Whoops. That's all messed up. Come on. Go. Whoa. Okay. Stat. Calc. Sine reg. Okay. One more time. Let's see if we can get the store regression equation. Nope. I didn't get the alpha key. Okay. So store it into y1. On the other calculator, just go sine reg y1. Okay, hit calculate. It's going to run the sine regression. On the other calculator, it's going to default to that 3, L1, L2. That's fine. You don't have to worry about it. Okay, so we've got rounded. We've got 2.15. So t of n is 2.15. Sine. Now note the form, right? So bracket 0.015. Oh, wait, 0.01, 0.02, I guess, if we're rounding. Now, you know, we're going to round for writing this out, but when we do stuff, we're going to use the calculator. It's going to actually have the proper value, because that's a lot of rounding there. Plus 1.88 plus 6.63. So plus 1.88 plus 6.63. Okay, so that's our rounded value. Use the calculator to determine the earliest sunrise time and the day it occurs. Okay, so we've got that. Let's go to the graph. Got a graph. We want the earliest, so what are we looking for on the graph if we want the earliest? We're looking for minimum. Okay, so we go to the calculator. We go second calc. We want minimum, which is 3. So to do the minimum, you have to go left bound. So I'm a little too far to the right. So left bound, and then right bound. Just means go somewhere to the right of the minimum. And then it wants a guess, and it just wants a place to look. Okay, and we get day 177 at 4.48. Okay, so what's that? You didn't put y1 in, I can't help you. Okay, so second calc minimum. So we get day number 177. And time of, what was it, 4.48?
Yeah.
Okay, yeah, 4.48. Okay, so when is day 177? So where are we going to start looking? You got a chart. It's got day numbers on it. Where you?
June and July.
Yeah, between June and July, right? So it's 177 minus 152, right? June 1st is day 152. So if we go 177 minus 152, what is that, 25? So we're going to get June 25th, right? We're 25 days into June. So it'll be June, oh no, wait, sorry, June 1st is 152, we're going to have to add one, so it's going to be 25 plus 1.
It's 25 days after.
Yeah, it's 25 days after, so 25 plus 1 gives us June 26th. That's 25 days after June 1st. So June 26th. And the time, so now we go 0.48 times 60, right? Because we got decimal for it, we need to turn that into minutes. So how many minutes is that? Like 29, it's a little shy of 30 minutes. So what's 0.48 times 60? Do I have to get my calculator? 0.48 times 60. 28.8, call it 29 minutes. 29 minutes. So June 26th at 4:29 a.m. Okay, so we built a model. We collected some data. The data it's probably freely available on the internet. The data is, and use Saskatchewan if you can, because they don't switch times. We collected some data. We had to adjust the data. We had to adjust Mountain Daylight Time into Mountain Standard Time to keep a standardized time base. We figured out on this day of the year, we created a, we did the sinusoidal regression. So that's a model, right? And it fits nicely. Those data points are pretty much exactly right on that curve. And we said, okay, what's the earliest sunrise? Well, okay, so June 26th. That's about the right time, right? Longest day of the year should be June 20th, but we're offset a bit because we're north of the equator. Okay, so day 152 is June 1st, so I'm 25 days after June 1st. So we're on June 26th. Okay, so we were 177 minus 152, so it's another 25 days, but it's 25 days from the 1st, which is June 26th. And then we had the decimal time, 0.48 times 60 to convert decimal time into minutes, gave us 29 minutes, so 4:29 a.m., right, which in Mountain Daylight Time would be 5:29 a.m., so it's not. The farmers in Saskatchewan like to get up really early, right, it's 4:29 a.m. Okay, what else? What 2 days will sunrise be at approximately 8 a.m. Mountain Standard Time? So, how are we going to do this one? Yeah, so in the one we just finished, given, excuse me, we were given an x value, and we had to work out the y value. Right? Oh, wait a second. No, sorry, we did the minimum. So on the one we just did, we did the minimum. Here, we say, I know what time I want. I want the time to be 8. And you notice you've got the full equation in here, like to about 124 decimal places, or like a lot. So here, we're just going to put in 8. Okay, and then we're going to graph that. So at 2 times during the year will the sun rise at 8 o'clock, right? So the first time says, okay, so we're going to go second calc, and we want the intersection, right? And we're interested in, and actually I'm just going to move along the red line. We're interested in the x coordinate. We don't care about the y value. We know the y value is 8. We're saying, what x value gives us a y value of 8? So we're interested in, hey, what's the x value? Okay, so 1, 2, 3, intersection, 35.74. Okay, so we'll say it's on day 36. And the other day, so second calc, intersect again. And again, I don't want to go along the blue curve, like not on this anyways. On yours it's not as big a deal. But I'm just going to shift it so it goes along the red curve, because that's a straight line. So day 36. And it says approximately 8 a.m., right? So it's never going to necessarily be exactly 8 a.m. And 318.74, so days 36 and 319. Okay, so what do? We set y2 equal to 8, and we did second calc intersect. Okay, what day is day 36? Okay, well, I don't know. So day 32 is the first, 33 is the second, 34 is the third, 35 is the fourth, 36 is the fifth. Yeah, right. What you said, right? Because what are we starting at? We did February 1st, so you could go 36 minus 31 is 5, and then 31. Oh wait, so 32. 36 minus 32 is 4, and then February, so 1 plus 4 gives us February 5th. And day 319, what's our reference point for 319? It'll be November 1st is 305. So 319 minus 305 is 14. So we got 1 plus 14 is 15. So November 15th. And those are actually both standard times, right? Those are months that are in standard time, so it didn't change. There's no daylight time to worry about converting. So February 4th, 5th. Go. So if you have the calculator, you can do alpha F4 enter. If not, vars, y vars, enter, enter. Hit the vars key, arrow over to y vars, hit enter twice.
So I have, yeah, so mine, when I do the sine regression, it like skips that sort of menu.
Okay, so if you just want y1,
Yeah, but
go sine reg and go vars, y vars, enter, enter.
I did that and I got a slightly different equation than you.
You must have a different number, different.
That point is that.
Get that? Everybody else get the same equation rounded to 2?
Yeah.
So I would say one of your numbers is a little off. Would be all like you'd have to go back through the table and just check all the numbers. From January 1st to December 31st, how many days have a sunrise time after 7 a.m.? Okay, so in this case, what are we going to do? Same thing we just did, really. Right, but put a 7 in there. Figure out those 2 days, right? And then say, okay, so sunrise time after 7. So you could figure out how many days are in here and just go 365 minus that, right? So if you know how many days are in between, how many days have the sunrise time after 7, you know there's 365 days in the year. So you can just figure that out and subtract. Okay? Or, I mean, you know, this date here is going to give you how many days, right? This first one here, if that was day 70, you'd say, okay, there's 70 days here, and then you just go to this one and go 365 minus that plus 1 to get how many days are here. Right. So you could do days in the tails, right? There's like so many days in front, there's so many days at the end, right? Which requires a fancier calculation, or you do days in between. There will be no day that's exactly equal to 7. Yeah, exactly. Okay, well let's find them and see what we get. So let's, whoops, come on. Second calc, intersect. Let's go up here. So somebody needs to have a sunrise after 7 a.m. Okay, so that's day 68.1 has a sunrise at 7 a.m. After 7 a.m. is going to be before that, right? Like above. So we go with day 68, right?
Yes.
So we'll go 68 days. It's on the 68.1th day. Okay, that doesn't happen. Day 69, the next day, we'll have a time before 7, right? So after 7, we're at 7 at 68.1, so we use 68. So here we use 68. So y2 is equal to 7, and we do a second calc intersect. and we get day 68.1. So 68 days. So the first 68 days, let's say this. So the first 68 days have sunset after 7. Right, so a higher number. Okay, and then we go run it again. Second calc intersect. Let's move to the red line. Move across. Move across. Move across. And one more. So this is 286.3. So what's the first day we're going to get a time after 7? Day 287, right? So day 286 is going to be just below the line. Right? So if you look at the direction we're traveling here, we're going up here. It's approaching 7. If I went second calc and threw in day 286, well, let's do that. So we're just going to say day 287 here. So day 287. Come back. So if I went second calc value and said, show me the time on day 286, and it comes back 6.98. It's like, that's really close to 7, right?
Yeah.
It's not quite. It's probably mere seconds away, but it is still before 7, and we want after 7. And so we know that there is no exactly 7, right? Not on a particular day. So, but we say on day 287. So we need to get how many days from day 287 to the end of the year. So the way you do that, if you're counting, and we're including day 287, the calculation looks like this. We go 365 minus 287 plus 1. Because you got to add 1 because you want to include the 287. Right? Like if I want to say how many numbers are there from 1 to 4, we know there's 4 numbers, right? 1, 2, 3, 4. If I go 4 minus 1, that's 3. I have to add 1 more to include. Okay, so we go 365 minus 287 and then add 1, so you're actually including that day.
But when you calculated that day, it was below 7.
No, day 287 is above. I did 286.
Oh.
I said, what's the time on 286? Just to show you it was before 7. If I do 287, let's do that. Second calc, wrong one. Second calc value. If I throw in 287, it's going to be after 7, 7.02. Okay. I mean, either way, they're really close to 7, but that's after 7, and the 6.98 is before 7. Okay, so what do we get with 365 minus 287 plus 1? So we're going to do 79. So the first 68 days of the year and the final 79 days of the year. So total days will be 68 plus 97. So total days, 68 plus 79 is 147 days. Excuse me. So on 147 days, the sunrise time is after. That's depressing, isn't it? It's like if you got to be somewhere at 7, you got a job, you want to go work out or something. It sounds like the sun won't be up.
Oh, is this going to be like multiple choice?
Doesn't look very multiple choice to me. But on the exam, it'll be like multiple choice.
Here, I'll find one day here.
Oh, okay. If we give this as multiple choice, they generally don't give like 146 days, 147, 148, 149. They're usually split out a bit more. But that's in 30-2 where we're actually nice to students. So in 30-1, they'll probably give you the actual. So these are exercises for you to do, and then we're just going to pop into the next applications and take a look at example 1. So what we just did was we ran regressions, right? Given a set of data that was collected, we saw that it was in a sinusoidal pattern, or a wave-like pattern. So we say, hey, we can model that with sinusoidal equation. And we ran a sine regression, put the data in the calculator, ran a sine regression, came up with the equation, and then used that to find different characteristics. Here, the maximum tidal height at a port on the east coast of Nova Scotia is 4.2 meters at 6 a.m. Minimum height is 1.2 meters at 12:15 p.m. Relationship between tidal heights and the time in hours is sinusoidal. Sketch a graph for height as it relates to time. Graph 2 full cycles. Okay, so let's call this 1.2 and call this 4.2, right? So we have a max and a min. And I'm just going to sketch just a little dashed line here and here, so that I know that my curve lies between there. So what's halfway in between there? So D, the average, right? So D is equal to max plus min over 2. Okay, so 4.2 plus 1.2 over 2 is 2.7. Okay, so here we go. So we've got D is equal to 2.7. Right? We can label that over here. So if I'm working out, because we're going to state this equation, right? So we already know one of the values. Oh wait, we know two of the values. What's the amplitude? So A is equal to max minus min over 2. So if I want to calculate it, right, so it's 4.2 minus 1.2 over 2, which is 1.5. Or you just say, how far is this, right? Oh, that's 1.5. Then this better be 1.5. As long as they're both 1.5, you're good, right? Because it's got to be halfway in between. So we got D, we got A. All right, now what? Okay, we got 4.2 meters at 6 a.m. Okay, so I'm going to need a scale here. And then the minimum is at 12 p.m. So how long, so from a maximum to a minimum is how much of a period? Half. And how many hours is that going? We're going about 6 a.m. to 12 p.m. It's like about 6 hours.
Yeah.
Okay. So then the period's about, that's half, so the period's about 12 hours. So we need to graph about 24 hours, right? So I'm gonna, my scale on the bottom is I'm gonna go up to about 24 hours, right? So I'm gonna go by twos. That'll hit the 6 quite nicely. That'll hit this relatively closely. Okay, so 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. Okay, so 2. Okay, and this is time, so that's T. So this is time in hours. And this is height in meters, height in meters. Okay, and this is the h-axis. Okay, so we've got h, and we're going to do h of t, right? So height as a function of time. Okay, so we got 2 points. Let's plot those 2 points. So 4.2 meters at 6 a.m. And 10:10, 10:12. And 1.2 meters at 12:15. So I'm doing my best to get 12:15. Okay, so that's really 6 hours and 15 minutes, right? So how long is it going to take to get back up to the top? 6 hours and 15 minutes. That's going to be 18 and a half, right? Okay, so if you want, you go 18.5 and 4.2. Right, this is 6 and 4.2. And this guy here is 12.25 and 1.2. And what did we want? 2 cycles? So then, what happened 6 hours ago? It's actually going to be a little bit in the past, right? It's going to be like 6 hours and 15 minutes ago it was down here. Right? So that's negative 0.25. So if we use 0. Now negative 0.25 just means 15 minutes before midnight, right? So 15 minutes before midnight. So if we're going to do, so I got 1 complete cycle, and I need to come back down again, so I'm going to add another 6 1/4, so that'll take us to 24 3/4, and that'll take us down here. Okay, so this will be 24.75 and 1.2. Okay, and now I can sketch out my. And if I want these guys, they're just halfway, right? They're 3.1, what's that? It's a quarter, it's like 3.125. Yeah, I don't want those guys that badly to figure out the times, okay? These are good enough, okay? So we got a pretty decent sketch of a sinusoidal function, okay? Determine the equation that describes in each, so we want, the first one is a cosine function. Okay, so as a cos, all right, wait, we need b, right? So what's b? So b is equal to 2 pi over the period. What's the period?
12 hours and 30 minutes.
So 12.5? Okay, so we've got to go to decimals, right? So 2 pi over 12.5. So as an exact value, you go pi over 6.25. Or leave it as 2 pi over 12.5. Looking here to see what do they do. What do the ubiquitous they do? Actually, the wrote is 4 pi over 25. I guess it's cleaner to just take out any decimals, right? So let's just multiply it through by 2. So 4 pi over 25, right? Just double these guys. Okay, so now we can do our equation. As a cosine curve, is A going to be positive or negative? I'm going to make it negative and just kick it to the left. Yeah, I'm going to make it negative and kick it to the left 0.25 hours, right? 15 minutes. Why not? So h of t is equal to negative a, so negative 1.5 cos 4 pi over 25 t, it's going left, so that's going to be what? Plus.
Negative.
Well, so just plus 0.25. It's going left. To me, I just look and say that goes left 0.25, right? And then what's d? Plus 2.7. Okay. So there's your cosine curve, right? It shows, hey, I didn't say a had to be greater than 0, did it? No. Okay, if it did say a has to be greater than 0, then h of t is equal to positive 1.5 cos 4 pi over 25 t. Okay, the maximum was at 6, so this will be minus 6 because it's right 6 plus 2.7. Okay, so there's two possible cosines. I think if it doesn't state what a has to be, you're open. As a sine function, so let's do the two sine function. So this is, let's just do the one. This is kind of the obvious one, but now we got to figure out what that is. So what's this? I'll put in the other stuff, right? It's just a sine function. So 1.5 sine 4 pi over 25 t. It's going right, so it's minus, and it's not 3.
No?
Not exactly 3.
Well, isn't it 6 minus 0.25?
So the period is 6.25, right? So that's going to be a quarter of the period. Or sorry. The period is 12 and a half. That's 1/4 of the period back, so it's a quarter of 12 and a half, which is 3.125. Okay, so it's going to be 6 minus 3.125, which is 2.875. I think if that's right, that's almost amazing. So it's not 3, it's 2.875, right?
Well, yeah. Couldn't you just take 6 and subtract 0.25 and divide that by 2? The 2x value.
You could take 6 and add 0.25 and then divide that by 2.
No, but like you just.
Oh, yeah.
Yeah.
We can write that.
Yeah, you're right. You should be able to do that.
Yeah, because I got 2.5.
Yeah, 2.875.
Hold on.
Yeah, so it's 6 minus a quarter of the period, right? Okay, and the period is 12 and a half. Yeah, so just go 6 minus 1/4 times 12.5. So this is 6 minus 1/4 of the period. And the period is 12 and a half. Okay, so it's 6 minus 1/4. Wait, should be 2.87. Okay, so if you've got mins and maxes, right? I mean, mins and maxes give you D, they give you A. I mean, not for free, you got to work a little bit, right? But you can average them to get D, and you could take half the distance between them. So you can take the distance between them and divide by 2 to get A. If you've got min and max, you've got half the period. You could double that to get the period. You want to get the B value, it's 2 pi divided by that. Any decimals, get rid of them, just multiply by something. I mean, you can multiply by 10, but then reduce that. In this case, if we just said, oh, if I double the 12 and a half, we'll get 25. Okay, and then double the 2 pi. That gives you B, and then really, what are you worried about? Well, phase shift. Okay, and then that would be as a reflected sine curve, which nobody in their right mind would do. Because it doesn't make sense to do that. Like, reflected cosine curve makes some sense. It kind of pushes it back in time, but it's pretty close. A cosine curve makes sense. They gave us the max, so that was easy. Reflected sine curve to here, that's a bit of a pain, but it'll be 6 plus 1/4 of the period, and that'll just go in there, right? But everything else stays the same, right? Amplitude doesn't change, midline doesn't change, period doesn't. This is not the period. But the B value, period doesn't change, so the B value doesn't change, right? It's just a phase shift. Algebraically determine the tidal height at 8 a.m. rounded to the nearest tenth. So we have a function, and we must algebraically determine, so we want h of 8. So we'll use our 1.5 cos 4 pi over 25. Now I'm using the other one, it just has the 6.
Yes.
It's a little easier. It won't make any difference.
You're just substituting value.
Yeah, substitute that. I chose, let's go with this one. Because this is just 8 minus 6. That's easier to do than 8 1/4. 8 minus 6, bracket, plus 2.7. And so that's a 2, so it's going to be 1.5 cos. This is a 2, so it'll be like 8 pi over 25. You would have to evaluate that in a calculator, right? We don't have an exact value for 8 pi over 25, so we can't. And it's going to work out to, rounded to the nearest tenth, they said it's going to work out to 3.5 meters. So it's about equal to 3.5 meters. What does 4 pi over 25 do? What does the B value do in this case? It converts hours into radians. Okay, converts hours into radians, right? So that's what it's doing. Because you're giving the function a number of hours, and this has to say, but hey, this guy takes radians. I need to convert this into radians. So the 4 pi over 25 just converts the hours into radians. Determine the first time after 6 a.m. the tidal height is 3 meters. Okay, so that's just a calculator question. Right, so you have to graph this on your graphing calculator. So we're going to do graph y1. So it says determine means show some work, right? Or show your work. So graph y1 is 1.5 cos 4 pi over 25 x minus, was it plus? What are we doing? Minus 6 plus 2.7. Just get rid of that. So if I'm going to graph this, what was our window? I mean, what did we use? We said like 0 to 26 or something? 0 to 26 by 2s. And what did we go? 0 to 0 to 4.2? 0 to 5 maybe? 0 to 5, but 0.5 is good. Okay, y equals, clear this out. I'm just going to throw in the 2.7 because I just like to graph the midline, just for the heck of it, right? Because if I graph it, if it doesn't look right when I graph the midline, then I know that I either got that wrong or I don't have the midline. Or so 1.5 cos. I'm going to throw the 4 pi over 25 in brackets just because I like to. And then we've got x minus 6. And then we got to close that off and add 2.7. Okay, so I should just be able to graph that. So I'm going to take the midline out in a second because we're going to throw in that 3-meter line. But this is just to look at. So I should see about 2 cycles, a little bit more, right? Because we went to 26 hours. A little more than 2 cycles. Okay, that's midline looks good. Okay, let's go change that. So we'll go y equals 3. 3. 3. Okay, graph that. Now, no, it's asking the first time after 6 a.m. Okay, so which time? We don't want this time. We want this time, right? First time after 6 a.m. This is 6 a.m. So that's the time where. So if you got a number and it was lower than 6, then you know, oops. Right? I want. Okay, so second calc, intersect. And I'm going to kick up to here, and this is the guy that I want here. So 1, 2, 3. Okay, 8.72.
Yes.
So 8 hours, 0.72 of an hour. Okay, so what else? y2 equals 3. Find x coordinate of intercept. That's coordinate of intersection. So t is equal to 8.72, which is 8 hours and 0.72 times 60. 43, 843. Yeah. 843. Okay, good enough.